אתה הולך לחזור היום קצת אולי על ה-EM אלגוריתם?
לא התכוונתי.
אוקיי.
אבל... אני יכול לענות לכם דמו. עושים עוד דמו?
כן, עם כזה הסבר של מה קורה שם.
טוב. תקשיב?
כן. כי רוצים לו קצת כאן. לקרוא להם?
כן, בטח.
אני יכולה לתקשר עם כל החבר'ה מאירופה. יש לי מספיק שפות בשביל... יש לי מספיק בשביל כל המזרח אירופה. יש לי ספרדית בשביל כל אירופאים שיודעים מה. לא משפט, כאילו, לא, אני טיילתי עם עיניים. שבועות, אני לא יודעת. Bueno, ¿da mucho? ¿Cómo se pueden dar la América que voy a ver? Ahí es.
Okay, let's start. So, let's start easy with some demos and stuff, pictures. So, basically we're done with the parameter estimation part. Sorry I couldn't be here last week, I was in the delivery room. And this is okay. So, right. So, if you have questions about that part, let me know, or Roy, and we can help out. I do want to show you just a demo of EM, just so you see how that works when you program your thing. You can see that it does something similar. So, as Roy mentioned, EM is an algorithm for, let's say you have data, and you want to, you assume that the data comes from not, say, a single Gaussian, but a mixture of Gaussians, okay? So the way the data is generated is you have, let's say, 2 Gaussians, and at every sample you choose which of the Gaussians to sample from, okay? According to some prior probability, which is the CK parameter that you have. So let's say 0.7 from this Gaussian, 0.3 from this Gaussian. You decide which Gaussian to draw from. Each Gaussian has its own mean and variance, and then once you pick the Gaussian, you draw the point from there. Okay? Is that clear? So, for example, in 2D, what this would look like, ignore these green and red things. So this is a mixture of how many Gaussians? 2, right? Okay. So these blue points were drawn from this mixture of two-dimensional Gaussians. Okay. This is the mean of the first Gaussian. That there is the mean of the second Gaussian. What about their covariance? What do you think it is, more or less? It's more or less the same, right? And it's also spherical. Okay. So it has the same variance in all directions. Okay. So you know a bit about multivariate Gaussians. Do you? Okay. You know enough to accept that this has the same variance in all directions.
Right? You said something about the covariance.
Well, it's multi-dimensional, right? So it has a covariance matrix. So the covariance matrix in this case would be what?
Diagonal?
Right. Okay. But when you program it, you will also allow a non-diagonal covariance. Okay. This is for cases where the covariance is not diagonal. You can get shapes like ellipses. Okay, along the ellipses. Okay. Anyway, so sorry. This x1 and x2. This is two-dimensional. Okay. So the covariance is a 2 by 2 matrix. All right. Okay, and now you know this is the data that you see. It comes from, let's say you even know that it comes from a two-dimensional Gaussian mixture, and your goal is to estimate what? No, you want to know the means and the variances of the two Gaussians, or means and covariances in this case, and also the mixing proportions. Okay, so what is the probability of the first Gaussian and what's the second? Okay, this is what we call CK, the parameters. Right, and now you can do this in various ways. EM is a very nice algorithm for doing it. Roy described it, and you'll be implementing So what does EM do? What does it store at every point in time? The parameters, right? It's an iterative algorithm, and every iteration it stores the current set of parameters. What are the parameters? They're the probability, a priori probability of the Gaussians, the means of the Gaussians, and the covariances of the Gaussians. Okay? So at every iteration, EM stores these. And okay, and it updates them as it goes. So initially, I just set it up so this is the mean of the first Gaussian, the mean of the second Gaussian, and the covariance. I use this to draw well, you can intuitively understand this draws the this is a graphical illustration of the covariance. What this is in practice is an equiprobable line. It's a line. So all points along this line have the same probability. Okay? You understand? So in the Gaussian, in the red Gaussian, all these points have the same probability. Okay? Under this model. Okay? So what covariance did I start with? What does it look like? It's the identity matrix. Okay? It's again an identity covariance because it has the same variance in both directions. Okay? And they are independent, so there's no elongation. Okay, so I just started out with some unit covariance here and here. So you see it has the same covariance structure. Okay? What can't you see here?
You just
Sorry?
decide about any distribution?
Yeah. Well, the means and the covariances. Okay? EM.
Throw it. You just
Well, I randomly, when you work with it for a while, you sort of have good heuristics for how to choose it. Usually it makes sense to start with something pretty small, and so let's say mean 0, and well, not necessarily small, but you can start all of them from the same value and then just add some noise so that they're not exactly the same. If they're exactly the same, these two Gaussians, it's going to get you into trouble. Okay? So you want them to be a bit different. But you can play around with them. Okay. So this is my initial estimate. What's missing here? What can't you see here? Sorry?
Innovations.
No, I mean, what parameters of the model can't you see here? The CKs, right. The prior probabilities for each of the Gaussians, right? You just see the Gaussians. Right, okay. And now the algorithm starts and it does its thing. Basically, what it more or less does is look for every point, what is the probability that it comes from the green Gaussian and the probability that it comes from the red Gaussian, okay, under the current model. And if it and now you have two weights, right? So let's say the probability of this Gaussian given this point is 0.9 and of this Gaussian is 0.1, okay? Then this Gaussian is going to get a weight of 0.9 for this point, okay? So now when you recalculate the mean, you're going to use this point with weight 0.9 for this Gaussian, okay? You'll see it in the update expression. I don't want to get to it. Okay, so what happens after one iteration is this beautiful thing. So because the green Gaussian was here initially, was a bit closer to these points there, so it got a higher weight for these points. And now when we recalculated the mean, we use more weight for the green Gaussian with these points, and that's why the mean of the Gaussian was drawn in that direction. Okay? Okay? You see that the covariance is no longer diagonal. Okay? So this is illustrates the covariance, and you see that it's diagonal. Don't worry too much about how I do this thing. Okay? You won't need to, but it does reflect the structure of the covariance.
The covariance is affected now from the mixture of the two Gaussians. That's why it's diagonal in this direction.
Yes, exactly. It sees variance in this along this direction more than in this direction. Exactly, very good. This one is less excited, but I mean is less sort of diagonal because it sees mostly these points. Okay, right. So what will happen now?
the green will not there.
Right. Oh, right. Correct. Why?
Because all the observations near the red one will go to the red one.
Exactly. Very good. So some points here, for example, this point would probably be more drawn to the green one than to the red one, so it's still affected. Okay. But certainly all the points in the upper cluster will have much higher weight for the green cluster. Okay. Right. Note that these points do not go exclusively to one cluster. They always have a weight for going to either of the clusters. Okay. If they go exclusively into one cluster, what do you call that algorithm? Maybe you know?
Maybe.
Right, exactly. So there is a variant of this algorithm, I don't know if we mentioned this, where each point decides exclusively which cluster to go with, okay? And then we call that primitive, okay? So when the weights are essentially 1 and 0. But in EM, in correct EM, there's always weights for each of the guys. It might be very low. For example, this point is going to have very high weights for the red cluster and very low weights for the green cluster, okay? But it's still going to be some non-zero.
What was the name of this variant?
K-mean, okay? All right, so as predicted, I hope we'll see that's good, okay? See, so it still has some, because this point still has a non-negligible effect on the green cluster. You still somewhat allocated in the middle, but next looks like this, and more or less, I have some stopping criterion and it's done, okay?
Why do we need it? Like,
Why do we need it?
Just calculate the.
Don't you think this is a beautiful thing to do automatically? Why do we need what?
No, maybe I don't understand something.
Okay.
We have observations, and we don't know that they're distributed this way. Like we don't know that there are two cycles.
Yeah, I mean, if they have a 100-dimensional observation, okay? Let's say when you do in spike sorting, this is used, okay? So you have I don't know, like 200 milliseconds of spikes, so it's, of like the trace,
Yeah.
and then you want to separate it into different cells, okay? Then you don't see this nice two-dimensional drawing, okay? It's in 200 dimensions.
Okay.
And people are not very good at clustering things in 200 dimensions.
Okay, now I'm.
But algorithms are very good, okay? If you have documents, you want to cluster them into different topics. So for example, when you write in Google, I don't know, give me something with ambiguity.
Oh, yeah.
Jagger.
Well, sorry?
Jagger.
Jagger?
Jagger.
Jagger.
Ambiguity.
The car and the animal, right? Exactly. So what do? So when you have Jaguar, okay, there's a car and there's an animal, right? And there are many documents for each. How do they know to give you like the animal in the first answer and the car in the second? Because they cluster, more or less, okay? They cluster all these documents and they see that there are two major classes here, okay? They do something pretty similar to this to figure out what are the major clusters. And then once they have the cluster, this is very informative, okay? Right, so clustering, this is basically EM for mixture of Gaussians is essentially a clustering algorithm. Okay, it lets you cluster points into a small set of clusters. And that's very informative in many applications.
If there will be more noise, so
Mhm.
then it will be difficult to cluster them, right?
Right, exactly.
So then the error, I need to calculate the error, or what will be the error if there is some mistake?
So the algorithm doesn't care, right? The algorithm is a likelihood maximization algorithm. It tries to find the best fit for a given data set as a mixture of Gaussians. Now it could be that either it's not well modeled by a mixture of Gaussians, or it's well modeled by a mixture of Gaussians, but they have a overlap, and then it's maybe not they're not well separated clusters, and maybe it's not very informative in terms of interpretation. Okay, but that's also fine. Okay, there's a third problem that EM also doesn't find the global optimum of the likelihood. We've already mentioned that, which is an algorithmic problem, and there are some ways around that, but let's not worry about that. Yep.
But how do you know in the first place how many clusters?
Very good question. So there are. We'll get back to this I guess in 2 or 3 weeks. Okay. For now, for your applications, for the exercise, you just assume a number or try different numbers. But I can say two things. One is that if you well, let me just say one thing. Intuitively, what is the right number of clusters? It's something that fits the data. It's sort of the minimal number that fits the data well, right? You could say.
That's one option.
Well, it's one option, right? And why is it complicated? Because you only see what that fits the distribution well, not the data. Okay, the unknown distribution. Okay, so you would like to say something like if the true distribution is a mixture of two Gaussians, Gaussians, I want to choose 2. Okay? So intuitively, what you want is to fit it with the minimum number of clusters that gives you a best fit for the true distribution. Okay? And how to do that, we'll discuss in a couple of weeks. So let's not worry about that for now. Generally, it's a bias variance issue, right? The more clusters you use, why is it good to use more clusters? Why is it good to use?
Better, less error.
Right. You have less bias in a sense, right? Because you have a more complex model, right? Just like with the polynomials that we have. Okay?
If every point is a cluster, you don't have any error.
You have perfect fit, right? You have the maximum, the best likelihood you can. Exactly. But what do you lose? You lose generalization, right? If, for example, you put a Gaussian on each of the points, let's say that was allowed, you have very nice training likelihood. But if I now give you a new point here, what's its likelihood going to be? 0, right? If you put a Gaussian exactly with 0 variance on each of the points, then anything outside has 0 likelihood. Okay, so that's not great, right? So it's the usual thing. We'll come back to this again and again. Yep.
How many iterations did we see here? And can you try
4, 5.
4 and 5? And can you try to explain what happened each iteration again?
Let's do it again. So this is, we started out with this, okay? Now, at each iteration, what you do is you go for every point, you calculate the probability that this is the cluster given this point, and this is the cluster given this point, okay? So these are two numbers that sum to 1. And these will be the weights for the clusters for each of the points. So each point sort of tells itself how much do I like this cluster, how much do I like this cluster, okay? And now you use these weights to recalculate the means and covariances of the cluster.
But what do they know about the cluster?
Oh, they know the means and they know all the parameters of the current of your current model. So your current model has a mean and the variance, etc. Okay. So and there's and what's the missing variable here? The unobserved variable is which cluster did this point come from? Okay. So this is the random variable, and we can ask, given this model, okay, what is the probability of this unknown variable being green or red? Okay? And this is something, given this model, you can calculate this thing using Bayes rule. It's very simple. Okay? You just plug in the numbers. Alright?
Yeah.
And then, after you have these numbers, you recalculate the means and covariances of everything using the updates that you saw in class. Okay? And they should be fairly intuitive to you. But I'll be happy to talk about this further. Anyway, so after one iteration, the means have changed, the variances have changed, the covariances have changed.
So
Yep.
although we don't see it, it already, the program already knows the means of the green circle.
Yeah, this is the mean. This is what you have after one iteration. These are your model parameters. You have the red mean, the green mean. Okay, this is your algorithm knows this. This is what you keep at every iteration.
So the mean is updated every.
Yeah, yeah. And then you use the new thing. Okay? So at every point you have your current estimate of the model, which amounts to these things, plus the C probabilities. Okay? And then you use them to re-estimate.
But just, I thought that before you said each point decides what's the probability for it to belong to the red circle or to the green circle.
Right.
So how can you do it without a mean? If you
Right. No. So at iteration T, you have the green cluster at T and the red cluster at T. Okay.
Mhm.
The green mean, the red mean at iteration T. Okay.
What are they at iteration?
At this point, they are this thing and that.
Okay.
You use those to calculate the weights of each point. Okay. You use the weights to calculate a new mean, the mean at T plus 1. Okay.
So every time you decide about more observations, more dots that belong to this distribution and calculate the mean according to them?
No, at every iteration you look at all the points. For each point you calculate its two weights. Okay? You use these weights to estimate a new mean for the green one and the red one. Okay? Yep.
In the step where you decide for each point which cluster, where you calculate the weights for
Mhm.
each point in each cluster, do you use the weights that each cluster has?
Yeah, you'll see that it comes into it.
Okay.
Right. Yeah. You essentially multiply that by this way. You should look at the update equations. If you have questions, let me know. But you use everything. you didn't use anything, something wrong. Unless you assume that the CKs are say 0.5, and then you're not going to optimize. Okay. So I think this is it for EM. I just wanted to do this demo. Any demo that I work on, I have to show, because then I feel bad that I justify that I prepared it. Okay, so this is one. With that, we are done with the parameter estimation chapter. I do want to tell you about another method, very common for estimating distributions. Okay, it's called the non-parametric approach. Okay, or non-parametric density estimation. You heard about this? Okay. So let's say, so there's something sort of maybe not satisfying about the way we did this so far. We said there's an unknown distribution in the world, and I'm going to assume that it's let's say a Gaussian, or that it's a mixture of 5 Gaussians. Okay. Whereas in real life, that's probably not going to be true, right? If I now look at the distribution of number of neurons in the brain, okay, across the population, it's probably not going to be an exact Gaussian, or it's not going to be Gaussian Y, the number of neurons. Right. Right. So it might be approximately a Gaussian. Or if I look at the distribution of psi count, it might be sort of cross-on, but not exactly. Okay. So generally, distributions do not obey this perfect unless it's statistical mechanics. So generally, in the world, if this is X and this is well, let's say P of X. Let's say this is discrete. Okay. So there is some unknown distribution in the world, right? And I'd like to model it. Okay. Right. What do I see? How do I? What's the information that I have? We usually assume that I have some IID samples. Okay. All right. Okay. So the problem with our approach thus far is that even if we have a lot of data, let's say an infinite amount of data, and the distribution does not come from our model. Let's say we assume Gaussian, but the true distribution is not Gaussian. Then even if we had infinite data, we're not going to find the true distribution, right? Because we're stuck with these nice belts that don't look like anything in reality. Okay? Right. So there are methods called non-parametric methods that take a different approach and say, more or less, I want my model to be more refined as I get more data. Okay? So I want to get a better and better estimate, or more refined estimate, as I get more data. And there are two sort of principal ways of doing that. So I just want to mention them very briefly. We'll talk about it in later class. I just want, since we're closing this parameter estimation bit, I do want to mention that. So I'll just show the figure, and it'll be clear what it does. Okay. So one option, let's say this is the red thing is the true distribution, and I just assume that the true distribution is what? A Gaussian. So it's actually idiotic in this. For the intro that I gave, it was just easiest to prepare. So here the true distribution is Gaussian, and these are the points that I see. Okay, so I have 5 points. Okay, these 5 stars here. Sorry, 1, 2, 3, 4, 5. Okay. Right. And now I take a different approach to modeling the density in this case. I say I'll partition the real line into bins, okay, of this width, okay, and for each bin I'll count how many points fall into that bin, okay. So what do we call this? A histogram, right? So why do we have 0 all here? Because there are no points here, right? Okay. So here I just decided to use bins of a particular width. Okay. So if I have 10 points, I get something like this, and 20 points, I get something like this. I'm always using the same bins. Okay.
What happens? How does the red line being updated?
Sorry? No, it's not. It's the truth. You don't see it in reality.
Okay.
Okay. Okay. So if I have 100, it's something like this, and So, right. So why is it good? It's good because when I draw use these small bins, I can capture maybe arbitrarily complex patterns. What's the problem? How should I choose the width of the bin? What happens if it's too wide?
You cannot see.
Right, I'm missing structure, right? What happens if it's too narrow? Right, I basically overfit, right? Because I look at too small windows. Okay, so you could think, and this is what a non-parametric approach in this case would do, as you have more and more numbers, what should you do? As you have more data, what should you do?
Make the beam smaller.
Decrease the size of the bin, right? Okay, so that's one approach to modeling distributions using bins. And there's another approach. It's called the kernel approach. So have a look at this and tell me what the method is. Okay? So it's the same data again, 5 points, and this is my estimate now. So what does it look like I did? So basically what I did, yeah, it's more or less what you say. For each point, I put a Gaussian on it, okay? So each point gets its own Gaussian, and this is the sum of the Gaussians, okay? Where you see the blue curve, okay? So each point gets a Gaussian with some width that I decided on, okay? All right? And this is the sum of the Gaussians. Why is it a good idea? Because each point, there's certainly some mass around, some probability mass around this point. So we put a Gaussian there to note that there's a probability mass there, and then we just sum the Gaussians. Yep.
The outermost points have different heights, the Gaussians you put above them.
Yeah. No, the Gaussians are actually the same, but because they are, this point gets mass from the Gaussians of these guys as well.
Yeah, but the outermost, they should have the same.
No, they don't, because they see less mass. This one is closer to all these.
Yeah.
Okay? This point is only close to this one, so it gets less mass than the others. Okay? The one in the center sees all the Gaussians of all the others. Yep.
How do you know the variance of each Gaussian?
So I decide on it. Okay? So it's the same as the width of the histogram.
And this is only when you know that your true distribution is Gaussian.
No. This is the advantage is, and let me show you what happens afterwards. So I put a Gaussian on each point. I don't assume that the whole thing is a Gaussian. I assume it's like an infinite mixture of Gaussians, because each point gets its own Gaussian. Okay? So let's see what happens if you have more points. So you could model things like this. You see? Okay? Right? And then when you get more points, you get something like this. So this is with 50 points. Okay? Again, we put a Gaussian on each point, but why does it begin to look like a Gaussian?
Isn't the sum of a Gaussian a Gaussian?
No,
No?
not at all.
It's
No, this is this is not a Gaussian, right? It's a mixture of Gaussians. Okay? So a mixture of Gaussians is not a Gaussian.
Yeah, but
The sum of two Gaussian variables, this might be confusing for you. If you take two Gaussian variables, their sum is a Gaussian variable. Okay? But the sum of two Gaussian distributions, okay, is not a Gaussian distribution. This is a mixture of Gaussians.
these are random variables.
No, this is the distribution, not the variables themselves. I'm drawing a distribution. Okay? So this is probability in this sense. Okay? So I basically assume that my distribution is a mixture of Gaussian, where the mean of the Gaussian is the points, okay? And the variance is some fixed number. Okay, look how nice it is. Okay, so each point it contributes. It says sort of I have mass, and something around me also has mass with some width. Okay, and then we sum these things up, and look how nicely it comes to this.
The sum of Gaussians is a Gaussian.
Well, in this case, yeah, but generally it's not. Okay. In this case, the true thing is a Gaussian, because we want to approach that. But generally, you could model anything.
The normalized.
Yeah, but no, generally, even here, it's not a Gaussian, right? I could have, okay, I'll prepare for you post break something where the red line is not a Gaussian. Okay? Alright, anyway. So this is just so you know, so there are, this is called kernel methods for density estimation. It's a non-parametric method because we don't have a fixed number of parameters. Okay? The more points we have, the more Gaussians we have. right? So it becomes, it's like a mixture of Gaussian with the number of mixture elements is what? The number of points. Okay? Okay. Good. Okay. Just so you know. And we'll talk about these methods also later.
What was the name of the last
This,
problem?
the one before, is just histogram.
The histogram is also a kernel, just a uniform kernel, I think.
No, because you don't put a kernel around each point. You don't put something around each point. You count. Okay. In the kernel method, you produce a kernel around each point. That's the basic idea.
So it's not around the point. You decide.
It's just the binning. Binning. Okay. Yes. Right. Okay. Okay. This is that. And today we'll talk about something completely different. We'll get to learning. So, I always promise myself now that I have a new daughter, and it's only my second child, that I would observe. Oh, I said I was in the delivery room last week. That's what it said.
No English, no English.
Well, you
Sorry?
just told her that you couldn't come.
Okay. Right. So yeah. So she's 1 week old now, and I always promised myself that I would look at, how babies learn. The problem is when you're sleepless and that's not your major concern. It's not academic, and you don't really get to observe these things. But it is a fantastic thing, right? How they learn within a year, even a year, within the span of a year, they learn to do amazing things. That even most advanced machine learning algorithms can't. So, yeah. So we will talk about learning today and then a few next classes. So let's begin with an interesting example. So maybe some of you have seen this did in some other class. So I'm showing you examples of one client. Okay, this belongs to say class A of objects. Okay, and this is class B of objects. So browse at it for a while. You see a pattern. Just try to come up with classes. Can you see something? Pretty hard, right? Okay, and this is the test set. So you're supposed to tell me, is this say A or B? Is this A or B? Can you do it? Okay. Yeah, seems hard. Okay. I don't remember what comes up next, I think. Oh, okay. Right. So, now, what I'm going to do is just take the training samples, okay, and just move pixels around, like with these puzzles, with the squares. So I'm just going to say this pixel moves here, this pixel moves here, okay? I'm not going to add any information, I'm just going to change the locations of the pixels, okay? And now, this is what you get for the train or test set, okay? This looks much easier for you, right? I mean, obviously you know these digits, right? But even if there were some new digit, you could, it would make much more sense to you. Like if I had something like, something, okay? You could probably learn it with very few examples. Yeah?
But if you kind of turn each of the pictures in 180 degrees.
No, but I use the same shuffling for everything, okay?
Yes, of course.
What do you mean?
So the pixel changes that I made were for both, they were the same for the 6 and the 9. So you're saying if I rotate it with 180 degrees, so I have to rotate both. Okay, so the 9 becomes a 6 and the 6 becomes a 9. But fine, you'd still be able to discriminate between the two, right? That's the point.
9 and 6.
So to generate the pictures that we saw before, you applied the same permutation to each of these.
Yeah. What I did is just decide this pixel goes here, but it's the same. That pixel there also goes here. This change of names I did without looking at the images. I just decided to reshuffle the pixels once. Okay. This is like in this prism film. How do you say this word? The inverting glasses. Okay, you know this experiment that you put inverting glasses on people, and it inverts your worldview upside down. Okay, and you get used to it in what is it, like a week or something. Right? But if I did the shuffling, I've been wanting to do this for a while. I don't know what happened. If you do a shuffling, a pixel shuffle experiment, I don't know if you will survive that. Okay. Right. So why did I want to do this? First to get some humility or to generate some humility that we can't learn everything. Okay, so I think even people in this in neuroscience have this conception of learning as we can do anything. Okay, we have a learning machine, and we can learn complex, arbitrarily complex things, and it's will show also theoretically that that's not correct. Okay, we can't learn anything. So even here, this is something. It is a domain that you know, but I just changed the representation of it, and we're at a loss. Okay, and computers can actually do this very easily because they don't care, right? They have the advantage and disadvantage of not having prior knowledge. Okay, so this is from a data set of digits that algorithms like SVM can do 2% error or even less, 1% for digits.
But what do they measure?
So they look at this thing, it's a vector of 0, 1 numbers, and they try to solve this task using any learning algorithms. I guess most of you have learned perceptron or SVM and stuff like that. You apply it to this problem.
What's the task now?
It's to discriminate, so this is so the task in this case is to discriminate between 6s and 9s, okay? So these are 6s, these are 9s.
How are computers able to discriminate if they were so different?
This is smart. What?
But the sixes, it's not that they have one image, but
Of course, this is why it's hard, right? That the 6s are not, they're different, right?
computers are able to discriminate where it is unshuffled.
They don't care because most of, let's say, the naive implementation of SVM for this doesn't even use the names of it will have exactly the same output if you reshuffle the pixels because it doesn't look at relations between pixels. It doesn't use the pixel location, okay? So for them, it is actually of this. So I guess the goal is twofold: is to make you humble with respect to yourself, and to make you respect learning algorithms. Okay. So this is and this is the test set. Right. Okay. And so what we'd like to do. What we'd like to do is to understand these learning processes better from a theoretical standpoint, okay? And to understand why, say, these two representations of the data that I use result in such different performances for you guys, okay? Why does it matter that if you get the data in representation, in this representation or the shuffled one? Why can you do this? Why are you better in this representation? Okay? Do you have sort of an intuitive answer for that?
We're doing visual clustering all the time.
Well, okay, so what you're all saying is that you have good features for representing this thing, okay? And in this example, these features that you're using actually correspond to the true classes, okay? So the true class is something like, okay, there's a line here, more or less. It then takes a turn around, okay? And it completes a circle, okay? And this is how you describe this class. So you were lucky enough that the features that you use actually correspond to the true classes, okay? Sorry?
In this case.
In this case, right. So now we could play another game where I actually put a pixel, say, here, and I decide that every time that pixel is on, it's a 6. And if it's off, it's a 9, okay? And you'll be looking at these nice features of yours that you think are great, but you won't be able to figure it out because I've changed the rules, okay? So the intuitive answer for why this works is that you are using a representation or a hypothesis class, if you want, that fits the true rules. Okay. So the good thing in learning that happens, if it happens, it's good, is that the rules that you are working with actually fit the rules that nature has chosen. Okay. In this case, it's not nature; it's us, right? So, because we made up these features. Okay. So, sorry.
There are any mistakes when what our hypothesis is wrong what the nature has?
If you choose,
If there are any mistakes, can you give example if there are any mistakes like this?
how do you mean?
You mentioned that there are hypotheses, how we wake up in the morning, we know the features.
Mm-hmm.
There are any mistakes that we think something, but the nature is different.
Even if digits, someone can write
Yeah.
with a really
Handwriting.
unreadable handwriting and
Right.
wouldn't be
Right.
able to
would be one example. Another is, let's say, poisonous food. Okay. Why do they make why do they add gas to cooking? Sorry, smell to cooking gas. Because the features that you have, we have many features for detecting poisonous food. Like when something tastes disgusting, this is some evolutionary mechanism for us to avoid food that is bad for us. Okay. But we could have come up with foods or poisons, deliberate poisons that avoid this your detection mechanisms, right? So actually, animals do have they have good features for avoiding food that is bad for them. Features that are correlated with what is poisonous in nature, but obviously there are other kinds. Okay? Especially if we start making our own. Okay. You know what? Let's just take a break. Now and reconvene at 2:11. Okay. 10:58.
מחר יהיה תרגול?
כן.
כן?
הבנתי שיש איזה כנס, אבל אלא אם קורה פה.
לא, אבל יש כנס
אם משכתם באותה חוקיות, אז זה אפשר.
אני יש לי שאלה ראשונה, אמרתי לך, הקורס הזה והייתה לי בעיה שמאוד קשורה ל-association.
אוקיי.
אני אשתף אותך בהזדמנות. אבל יוצא ככה שהמבחן עם אלגברה, זה יוצא לי, זה לא, אני עושה גם אלגברה 13.
אלגברה ים? אחד? אוקיי.
למרות שאני יודע את זה, לא הספקתי ללמוד לאלגברה, הספקתי ללמוד לחד והיה לי שבוע אחד.
באיזה תואר אתה?
אני אולי שמציא. דוקטורט, אני רואה שם.
אז למה זה לוקח לך אלגברה?
כי הם מחייבים את הסטודנטים לקחת את האלגברה בשנה. אם כן, אפשר לעשות פטור בחד, באלגברה שני מבחנים. אני עשיתי בחד והיה לי שבוע ללמוד, עשיתי בחד, אבל באלגברה לא הספקתי. אז אני עושה את האלגברה.
זה אלגברה של מתמטיקאים כאילו?
כן, אלגברה של מתמטיקאים. אז יש לי שני מבחנים יום אחרי יום. אז אני לא החלטתי אם לגשת לבחינה של...
יש רק מועד אחד.
זהו,
אני לא יודע אם יש,
רק
נכון,
מועד
יש
אחד.
רק מועד אחד, אבל באלגברה יש שניים.
יש שתיים, זהו, זה מה שאני
חשבתי
חושב.
שזה התשובה בגוף השני.
אוקיי, אז זה מה ש... לא, רציתי להתייעץ איתך,
מה,
אוקיי.
לא נראה לי שיש לך בעוד?
כן. זהו. טוב.
לא אכפת לי אם אתה רוצה, האמת שלא כדאי.
מה חשבת להגיד?
אתה יודע לזכור אותי משהו, אוקיי, טוב. כן, לא, אני אומר, אם זה לא יסתדר לך, אתה יכול גם... התחלתי לא להאמין, כי לא בטוח שאני אלמד את זה שנה הבאה.
שנה הבאה, לא בטוח שאתה... אוקיי.
לא, אני אומר לך שאם זה ממש בעייתי לך, אתה יכול להיבחן שנה הבאה, אבל זהו, אני לא יודע בדיוק מי ילמד את זה.
לא בהכרח אתה תלמד את זה שנה הבאה?
לא בהכרח.
אוקיי. טוב. נשאל.
רציתי לשאול לגבי שבוע שעבר, בהגדרה של פיוון. אז זה כאילו זה האינפימום של איזשהו אלפא, ככה ש-X זה B1, והטסט סייז הוא אלפא. אז מה קורה אם נותן אחד?
אין אף אחד?
כן.
לא, אבל אז זה יהיה אם אין לך מישהו שייתן את ה... לא, כן, יש לך... אם הוא לא באזור הבחירה של אף אחד?
נגיד...
זה מקרה פתולוגי, בדרך כלל זה לא כי בדרך כלל זה מבחנים שהם מבחני סף כאלה והם בסופו של דבר יכילו את הנקודה שלך. זאת הנקודה בסופו של דבר תוכל לבחירה טובה, אבל לא נראה לי שזה מקרה ש...
כאילו, חשבתי על זה שאם אנחנו כוללים את המבחן שבו כי הרי צריך לבחור
שהוא
בין
מחזיר,
הרבה מבחנים שהוא תמיד
הכל,
מחזיר
כן, נכון.
H1.
ואז יהיה ה-p value יהיה 1.
אחד, כן. אוקיי, עוד דבר, אמרת שיופיע בסיכומים של השיעור ההוכחה של קריימר-ראו?
יש את זה.
לא. אני בדקתי.
אוקיי.
זאת אומרת, אולי יש, אין לנו באתר השנה את הסיכומים האלה.
אין לכם בכלל את הלקט?
כן, אין לנו את ה-lecture notes, יש לנו רק את ה-exercise notes.
אז לא
אם
הבאנו
אפשר
אותם.
לשים את
לא,
ה-lecture
בטח,
notes,
בטח.
אז
כן.
זה יהיה
לא,
ממש
זה היה
טוב.
אמור להיות שם, אני מצטער שזה לא.
יש לקצ'ר 1 ולקצ'ר 2.
אתה רואה?
למרות שזה די כולל את הקריימר-ראו.
לא כולל את ההוכחה של קריימר-ראו.
רגע.
היה שם, לא הבנתי אותו, אבל היה שם משהו בסוף.
בואי נראה שנייה. זה
הסתכלתי בשלוש.
זה מה שנקרא parameter estimation,
הסתכלתי
נכון?
בשלוש.
רגע.
אולי אני טועה.
Efficient information,
יש את זה.
flow
מה זה,
function,
lecture 2?
camera theorem, proof camera.
כן, אבל זה היה תחת lecture 2?
כנראה. זה היה שם את כל הדברים האלה?
הרבה יותר כיף להגיד.
תבדקי, אם את עדיין לא רואה את זה, ונעלה גם את האחרים.
לגבי מה שהראית עכשיו, יש איזה, זה כאילו זה מאוד יפה, וזה קצת באוויר.
לא, בטח, אני חייב לעשות את הלמידה.
לא את הלמידה, את לפני זה,
על הפרמטרים או את
זה לא פרמטרים.
זה לא פרמטרים, נעשה קצת בקטע של מודל סלקשן, באמת בשביל לדבר על מה הרוחב של הגאוסיאנים ודברים כאלה, כן נעשה את זה יותר קונקרטי. רק רציתי כרגע, כי אתם רואים את הפרק הזה, שתדעו שיש דבר כזה, כזה טוב
יכול לספר לך על הבעיה של הקלסיפיקציה?
בואי, אני רוצה לעבור שנייה משהו, אז אפשר אחרי השיעור, בסדר? Okay, so as far as in that sense, what we're going to talk about is how to learn to classify things, and how to think about generalization error in this case. Okay, so here is a running example I will use. Let's say we play a game. So we'll talk about mostly cases where we have two classes. Okay, so our inputs are of one of two types. We usually denote those by plus and minus or by 0 and 1. So the game is going to be such that I give you instead of a positive points, instead of a negative points. Okay, this will be your training set. And now your goal is to provide some rule for classifying points into plus or minus. Okay, all right. So, all right, and let's say just for now that the rules that we choose, the rules that you get to choose are rectangles that are aligned with the axis. So you're allowed to give me a rule like this. Says, okay, you look at the point. This is the rule that you come up with. Is that fine? Okay. Right. So this is one option. You could come up with this option, right? Or you might choose to be, adventurous and choose this one. Why is this not a great choice? So you make errors, right? So it seems like, why would you want to make errors? It's not, actually, it's not strictly true that you don't want to make errors, and we'll talk about that later, but it still makes sense that you would choose something like this, okay? All right? All right, just in terms of notation, each point like this, I will call an xi, yi pair, where xi in this case is the point itself, and yi is plus or minus, okay? All right? Okay. So I have x1 to xn, this is my training set. What you output is this classification rule, okay? What is this technically, this classification rule? Well, it's a function, right? It's a function from the input, x, to what? To what, right? So you will give me an age that is a function from x to y, where x is, in this case, r2, and y is plus minus 1. Okay? That's the game. Now, what happens? What do you really want this your classifier to achieve? On what? Are you happy with this? Can we go home now? Because you say, okay, listen, I've gotten all this correct. I'm happy with myself. Right. You want to, essentially, this is what you learn from, right? But you want to be good on future examples. So if I give you 5 foods and I say, okay, this one is poisonous, these 4 are not, and you say, okay, I have a rule that anything in a blue bottle is poisonous, okay? Or let's say the poison is in the red bottle, and all the others are in non-red bottles. Okay, so now I have a rule saying everything is in a red bottle is what did I say? Okay, anything that is not in the red bottle is not poison. Okay, and that probably wouldn't be that great. Okay, so what you really want is to generalize to new examples, right? So the game we play now, after this is the first phase of the game. The second phase of the game is when we test it. Okay, so you fix this thing, say this is this is my rule, and now I come up with a whole slew of examples, infinite number of examples. Okay, and I test you on it. Okay, so now I draw this example. Let's just use a different color. And I say, well, this is actually a minus. And draw this example, this is a minus. Draw this example, this is a minus, minus. And here is the plus, etc. Okay? And we draw an infinite number of those. Okay? So essentially, we can think of a case where actually the true rule, the rule that I had in mind was this. Okay? All right? Right. And now the loss that you suffer is going to be the number of your expected error in this game where point is rectangle. Okay? So essentially, if I draw an infinite number of points, what is your error going to be? It's everything in this region, right? This is what you're going to get wrong. Correct? Okay? So the probability of error is going to be the probability that you see a point, that I sample a point in this red region. Okay? Okay, so this is just as a running example, so let's make this more formal.
So isn't it going to be reasonable to say that it's smarter not to assume anything about the red area, or maybe to assume something else?
What will you do with this assumption, either way? I mean,
You can say, for example, that for the area you don't know, you decide according to the probability, to the distribution of minuses and pluses in the whole.
okay, so you're offering a different, you're saying don't use this blue thing. You're saying now that I've learned this thing and I've looked at how you're going to test me, I want to try a different strategy, okay?
I'm still saying that I have this small rectangle where I know that it contains only pluses. And I have outside of the big rectangle when I know that it's only minuses, but in between I don't know anything, and thus I make decisions wrong.
But you have to give me an answer, right? It is your obligation to give me a function h that for every point here gives an answer. Okay? You have to say plus or minus. You can't say I don't know.
The function has to be defined similarly for the whole
No, you
space.
can do whatever you want.
So I can take another function for this area and say there I'm going to answer
Yeah,
according to that.
I'm just saying for simplicity, let's assume that you have to use a rectangle. It's not that ludicrous because I'm actually willing to play a game with you where I am choosing rectangles. Okay, so the true thing is a rectangle. So it's okay to use rectangles, right? Because the true answer is in there. But you don't know, obviously. But that's, okay. This is where the difficulty is, right? The difficulty is that there is in the world this red rectangle. You don't get to see it, right? You only get to see these labeled points. And you have to come up with something that will try to come close to the red one, okay?
You can update, by the way, every step.
Of course, but we're going to play, okay, I'll give the definition to you. Okay, so here's some definition. Yeah.
It's not obvious that the best idea is to choose a rectangle, like we saw before in the interpolation.
Correct. Right. So we'll use more and more refined notions of learning, okay? And so let's just get the notations right. So we'll assume there's the input space x, which in this case is in our running example is R2. Okay. These are sometimes called features. So for example, in the image that I showed you of the digits before, what's this vector x going to be? What's the input space? Sorry? It's a set of the values for all the pixels, right? So if I have a 16 by 16 image, it's 256 numbers. Okay? They were actually 0, 1 in that case. So now the output or label space y. We will assume binary classification. So binary. So y in our case would be just plus 1 minus 1. We'll sometimes do 0, 1, but it's binary. So most of the things to understand about learning you can understand from the binary case. So we'll just use that for simplicity. So obviously it could be non-binary, right? For example, for digits, what's the size of y? 10, right? Okay. Right. So these are the x and y. And then we said we see a training sample, which I'll denote by S, and it contains n pairs of labels x1, y1 to xn, yn. Okay? So, okay. And we will assume, for the sake of analysis, that these are samples d from an unknown distribution pxy. Okay? So pxy, what is pxy in this case? In our example? The unknown thing that I sampled the pairs from? Is the red rectangle, right? So I sample a point in R2 and then I label it, so this is like that we don't see. Let's say I sample a point uniformly in some area of R2 and then I label it using the red rectangle, okay? 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 So the way that these points are generated, x and y, there is some distribution pxy that is used to generate them, and this is the unknown rule, okay? Is that clear? Okay, it's sort of the most general way of thinking about how pairs of points are generated. Okay? So for example, if we assume general pxy, it could be that a particular x, so a particular point here, might be labeled plus in some cases and minus in others. That's right? Because py given x doesn't have to be deterministic. It doesn't seem like it's clear.
How will you formalize this rectangle?
I will say that there is so for example, in the rectangle, let's say p of x draws a point in, I don't know, let's say let's say in this square, this is 100, 100, minus 100, minus 100 uniformly, okay? So this gives us xi, alright? And labels it using what? Using what? The red rectangle, okay? Okay, so the simple way of saying it is that you have a set of points xi, yi, endpoints that are just drawn from a distribution on x y pairs, right? This is like the most general way of thinking of a probabilistic model for these. Okay? Often, these points will be generated by first sampling a point here, okay? And then labeling it using some unknown rule, okay? Which is the case here. So it is, you can think of it as partitioned into two things. P of x is the distribution of the features, okay? And then P of y given x, okay, is how you label the input. So this is the labels is, so P of y given x, in this case would be what? If we're looking at that, P of y given x would be 1 if x is in rectangle, right? And 0 otherwise. Sorry, it would be
Py equals plus.
right, sorry. The probability that y equals plus given x is 1 if it's in the rectangle and 0 otherwise. Okay? But note that this notation, the fact that we said that it could be a general pxy, we could also talk about cases where this is not necessarily 1 or 0, it has some noise. Okay? Okay, this is sometimes referred to as label noise. Okay. So generally there is a distribution pxy that has generated these things for us. I think it'll be useful for you to think of this distribution as something that first generates the point x and then labels it using some labeling rule. Okay? Alright? Good. Okay. Okay. So what is the output of the algorithm? The output of the learning algorithm procedure is a function h of x where your classification rule. Okay. So let me ask you, this is a summary question about things you've learned. Had you known P of x, y, okay? Let's say I tell you what P of x and y is. What is the best way to choose age? What's the optimal age if you know the distribution P of x and y?
maximize the metric.
Well, yeah, but for this example, if I tell you what P of x, y is, how do you calculate the optimum rule from it? No, but if you want to, no, it's not exactly P of x, y, right? Because P of x, y might be non-deterministic. Okay? So let me tell you the answer, and you already know it. So let's just comment. Had you known Pxy, the optimal age would be to set hx equals argmax over y, P of y given x. Right? If you want to minimize your error in predicting y from x, you know from the second class or something that this is the optimum thing to do, right? Okay? It makes sense, right? If you know P of x, y, you want to know y given x, then you choose the y that maximizes the posterior probability. Okay? This is the math.
It's assume a loss function.
Right, as soon as it's 0, 1. Okay, good. Okay, so this is the game. The game is you see a labeled set of points xi, yi, and you choose a function h. Okay? Right. Now, typically, h will not be some arbitrary function. Okay, there are many functions from x to y, right? If we have, let's say, if x is R2, then there are infinitely many functions. Yep.
Could you explain again why this is the optimal age?
Yeah, so think of the Bayesian case, okay, where we said, okay, so how can we think of this? You see x, you don't know what y is, okay? And you want to tell me the value of y, okay? And you lose a point every time you tell me the wrong value of y, okay? So we said this is a Bayesian decision theoretic setting, okay? Where we said that the optimal thing to do is to maximize the posterior probability if you want to minimize your overall loss. Okay? Okay, let's not worry too much about that because I didn't. Okay. Okay. So the only other piece of component in the puzzle is that we will typically constrain h to come from some set of possible classification rules, which we'll denote by h, uppercase, and we call this set the hypothesis class. Did I do this? Hypothesis class. Okay? So it's the class of all possible rules that we want to consider. Okay, intuitively, why do we want to limit ourselves? Maybe? Why should we not just use all possible rules?
We have prior knowledge about what a good choice of classification rules were, then we should use this knowledge.
Right. And so naturally, if we know that we are playing a rectangle game, it sort of makes sense to use a rectangle. But we also do that to avoid overfitting, generally, right? If we use too complex, we'll see this a lot more formally, but intuitively, if we use a class that is too large, we run the risk of overfitting. Okay, and we'll show analytically exactly what happens, why that happens. Okay, so why do we overfit if we use a large class of a large hypothesis class? Okay, good. Okay, so these are the components, and now we just need to talk about how to evaluate our learning algorithm. So how do we evaluate? So as I said before, the evaluation game is you give me age of x, and now what do? I sample points from what? How do I test you? Right, so I use this distribution P of xy that I used to generate the training data to generate new data, okay? And then I test your error on that, okay? So we'll define the generalization error of hypothesis age as follows. So we'll denote it by E of age, but we'll use a subscript P, where P is what? The true distribution, okay? Because naturally it affects the generalization. This is what determines the generalization. And it's simply the sum over x and y of the probability that this pair will be drawn times, okay, so what happens? I draw an x and y. So let's say I drew this point here, and actually has a label, what is it? Oh, this is actually a plus. Okay. Let's say I drew this point. It's a minus. So what happens with this point? You lose, right? Okay? So every time you H predicts incorrectly, you lose a point. Okay? So what it means that we multiply this probability by your loss, which is the event. So I'll just say what the notation is, that age x is different from y. Okay? So I is the function that looks at, this is the logical expression, aj is not equal y. Okay? It's either 0 or 1. So I just returns that 0 or 1. Okay? So this here, if you drew points such that an xy such that you made a wrong prediction, this is going to be 1. If your prediction is correct, this is 0. Okay? So this is, what can we call this thing? It's your expected error, right? So this is the expected error when evaluating age on pxy. Right? Okay, good. So seems to make sense that this is what we want to minimize. Right? We want, when we play this generalization game, where I give you all these new examples and you have to classify them correctly, this measures your expected error, and you would like to make this what? Small, right? Right. What's the problem? Why can't you just make it small? Well, it's an even more fundamental problem. You don't know this thing, right? Okay? So we'd like to make this small. Small. But we don't know P. Had we known P, we could have just evaluated this thing for all possible candidate ages and what? All possible age in our hypothesis class, and return the one with the smallest error, right? That's the best we can do. Correct? Makes sense, right? But we don't know. Right, if I showed you this red rectangle, you could have said, okay, I'm going for this one. My blue rectangle is the red rectangle, and you would have gotten an error of 0, generalization. But like this stuff, you don't have it. What do you have? You have a very say limited view, as always in our setting, which is just these small set of observations, okay, or labeled data. is your tragic state where you have to infer from this small number of labeled points something about this rule that involves essentially an infinite number of points. Right? This rule has an opinion about every point in space, not just the points that you see in your training set. Right? Okay. So problem. So what do you suggest? So your h needs to be a function of only your label points. What do you suggest?
The best possible observation that we have.
Exactly, right. Sort of makes sense, right? You say, okay, I have these points. At least on these points, I'd like to achieve minimal error, right? Okay, so very good. So let's say it makes sense, or it seems to make sense, to minimize empirical error. So when I say empirical, generally in this context, it means something on the training set, on the data that you see. Okay, it's empirical because this is sort of like the measurements that you take. Okay, to minimize empirical error. Okay, or let's say perhaps a clear term is training. Okay, I'm going to use either training error or empirical error. Is that all right? So I'm going to define this thing. It's going to look pretty much like the other one. So it's going to be E of H, but what's the subscript here? S. Okay? And it's simply the sum over I. I, exactly, H of xi not equal yi. And let's make it 1 over n, so it's same scale. Okay? So this is the empirical error. Good. So now that we have this thing, what should we do? You choose the hypothesis that minimizes it. Okay? So let's say this suggests the following learning algorithm. So the algorithm will be look at the empirical error and minimize it over all hypotheses that are in what? Your hypothesis class. Right? Okay? And we want to denote the output of this thing by HSERM. Well, let me be, this is important here, so instead of equals, I will write it here. Okay, so min, I could have multiple minimizers, right? Okay, for example here, how many minimizers do I have? I forget about this thing. Right? Many, many. Okay, I have this guy, I have this one, I have this one. Okay, they all have an empirical error of what? 0. Okay, but there are many of them, and also who's in there in this set of minimizers? The real one, right? So let's just to annoy you, I will put it here. But obviously, you don't see it, right? It's in there. It's in this huge set. This is sometimes called the version space. Okay, the set of hypotheses that are consistent with the observation. Okay, so the red one is inside there as well, but you don't. You have no way of knowing that it's the correct one.
Zero error or minimal error?
So minimum. Generally, you won't necessarily have 0 error. Okay. In this example, where you are playing rectangles and the true rule is a rectangle, you will have 0 error always. Okay. Why?
Because we'll just choose, as we know.
We'll choose HXI is equal to YI.
Well, but why can you achieve 0 error
Because
in
we
this
know
game?
the real form of the
Well, because you know that it was generated by a red guy. You don't know the red guy, but you know that the red guy would achieve 0 on the training error, right? So there's at least one rectangle that achieves 0. So when you do the minimization here, we know that the minimum is 0. Okay?
so always you can.
Yeah, in this case. Okay.
No, in all the
Right, but you have to be, the condition for this always being 0 is that the decision rules that nature chooses for you, the red guys, are within your hypothesis class. Okay?
How could it be different?
Oh, what do you mean? I could now, let's play a different game, okay? You still choose rectangles, okay? But there's a different,
Very different.
different game. I've invented a different game for you, but you're not allowed to switch from rectangles, okay? And here is your training sample.
No, but
Give me 0 training error.
when I see this, I won't choose a rectangle rule. I will choose a rule that will zero my decision.
Okay. If you can use any rule, obviously you can achieve 0 error. If you limit your hypothesis class, okay,
Okay.
then
Definitely.
you will not necessarily achieve. Okay? You're saying I can always, assuming nature chose some rule, I mean, it did choose some rule, then I would choose the set of all rules, for example, and then naturally I will, I can get a 0 error.
This is
Okay?
a better way to do it.
Right? Well, no, because what is the risk of what you do?
Right?
What is the risk of your strategy?
And it's looking at all the private world.
Right, you might be overfitting. Will almost certainly be overfitting. Because here's the perfect rule for this, okay? I look at this thing and I say, oh, I've got a perfect rule. I'm just going to, wherever this says plus, I will say plus, okay? Where this says minus, I will say minus. And all other points, I'll just say something. I'll say minus, okay?
Okay.
So, it's perfect here, okay? But this is, we're going to make this precise. That's exactly what we want to achieve. Yep.
What is written there?
Here, this one is the sub in. It's Shayam.
What
This
is
one?
ERM?
ERM, empirical risk minimization.
Okay. And H is from what?
H.
No, under the minimum.
This one? This is the hypothesis class. Okay? So you choose a hypothesis within your hypothesis class, okay? That minimizes the empirical
Should it be argument or?
yeah. Sorry. No. It is in the argument. So the point is that there are many, almost always there will be multiple minimizers here, okay? And you're forced to choose one of them. Other than choosing one of them, you don't have any other information. What happens if you have a single minimizer?
We choose it.
Go ahead.
We just choose it.
Right, but then what do you know?
It is the real one.
Right, assuming that nature has told you in advance that it's playing
This
this. Okay, good.
But if we don't have one, so what will we do?
Sorry?
If we don't have just one, like if there is a group of minimizer, we just choose one.
Arbitrary. Well, what else can you do?
Maybe there is a magic.
I mean, you could come up with different. There are obviously a lot of variations where you have different criteria for choosing among those, but they more or less amount to just assuming a different hypothesis class. Okay. Eventually, you will always get to a place where you have multiple hypotheses to consider. They all seem, of the same quality, and you have to choose between them, and you have no a priori way of choosing. Okay. Right. So this is the game, and there are many questions we can ask in the context of this game, and this is what computational learning theory is about. Okay, so it's a huge field. So between computer science and statistics, it got a huge boost in the 70s from the work of Bartik and Chervonenkis, and then others in the early 80s, and still going on. There's a lot of beautiful theory, sort of a combination of probability, combinatorics, and algorithms. So we'll do some just to show you the flavor of results that you get. Okay, so here are some questions we might want to ask in this context. Okay, so the setting is clear, right? We see a sample. We'd like to minimize generalization error. We chose. I mean, this is just one strategy. Okay. Actually, tomorrow we will describe a different strategy, but this is strategy, so it makes sense. This is called the ERM strategy, which is empirical risk minimization. Okay. You're minimizing your empirical risk. questions you might want to ask. Ideally, the big question is that you want to ask is, I want to achieve low error. When is that guaranteed, right? Okay. You want to achieve low generalization error. When is that guaranteed? So intuitively, when is that? When do you think it might be possible? What do you need to achieve low error? Probably. What could make your life better?
If I know that the group of representatives in work is include the real one.
High number.
Okay, so all answers are correct. First, more information is always better. Okay, so you might think, and you would be correct, that if you see more and more pluses and minuses, it's going to give you a better idea of what the true class is, right? If I give you an infinite number of these guys, okay, labeled from the red guy. Okay, you're going to be nearly there, right? The more data you have, the better your situation is going to be. So naturally, we need a theory that tells us how data helps. Okay, so here are some questions. How many samples do we need to achieve low generalization error? So this will be EP ERM. Okay. So if we learn with ERM, how many samples do we need to achieve low generalization error? Yep.
This is right only if our hypothesis group includes the real.
Right. Well, the goal of achieving zero error is realistic only if our rules contain the true rule. Okay? The goal of achieving low error generally.
Does not depend on it.
Well, if you say I want to achieve the lowest error possible, okay?
But if I'm not playing the game in the same rules at all, so why would this help me? I think that the rule is rectangle, but the rule is
But more data. Okay, so we'll cover this in depth in next class. But intuitively, okay, more data helps you because it gives you a better picture of what's going on, right?
Yes.
So let's get back to this cunning circle game that I played with you, okay? So let's say this is the game, right? So the true rule is actually a circle. So this is the true rule, okay? And you're forced to return a rectangle, okay? So if I don't give you as much data, okay? If I just give you sporadic data like this, okay? You might choose this rectangle, okay? But if I give you more data, you'll still be limited to rectangles, but you choose the best rectangle possible for this thing, okay? And so this is a very important point that if we can't achieve zero error, we still want to achieve the best possible within our class, okay? Right.
It's possible for us sometimes if we have a rule we need to act according to make some manipulation over the data in order for the data to fit to our rules.
Well, you could think of variations like that where you want to remove, say, outliers, stuff like that. I mean, you don't get, if the data is clean, in the sense that it was generated by the true distribution, then you don't get to play with it in the sense of, you don't change reality, right?
No, like change the basis or.
Yeah, you could. I mean, there are obviously infinite amounts of variations on this, but there's still the basic idea that it was generated by something, and you are modeling it with something else. Okay, that will stay regardless of the variations you have. Okay, so how many samples? How does let's say size in brackets of the hypothesis class affect this generalization. Okay, so we say we have this intuitive notion that as ages increase, okay, what happens? We run more and more the risk of overfitting. Okay, as we use the larger and larger hypothesis class, it seems like something should work against us. Okay, why? Because we have more and more rules to explain the data with, and we might overfit. Okay. Yep.
Does the hypothesis class
Yeah, it could definitely. I mean, it's just a set of rules that you consider when.
So two Gaussian is a different rule than 10.
Yeah, for example. Yeah. Okay. So what else do you want to say?
Can you define what is overfitting in this?
Yeah, well, overfitting basically means that you have very intuitively that you have low training error, okay, but high generalization error, okay. So you work with a set of rules that allows you to reduce your training error significantly, but at the cost of increasing your generalization error, okay. So you give you explain the data, you give an explanation that is too specific to your training data, okay, and therefore you sacrifice generalization. But we'll show exactly formally what this means.
And
Okay?
examples for that in this. I mean, you said that if age is bigger, I
Mm-hmm.
mean, I don't really see how it all comes together. If I have more, bigger set of rules that I can
Mm-hmm.
choose from,
Mm-hmm.
how does it make my training errors more?
Ah, very good. Very good question. So let's get back to this game. Okay? And now let's say you can classify this with any rule. Okay? Not necessarily rectangle. So you don't know of rectangles. You don't know that this exists here. Okay? So you say, okay, I have all the rules that can classify this correctly. Here's one. Whatever is inside the squares, the circles, I will label plus. Otherwise, I label minus. Okay? It worked great here, right? But it's going to overfit badly, right? It's going to generalize poorly. Okay? Why? Because you chose something, you had too much expressive power. Okay? So expressive power is both a blessing and a curse. And you fit this perfectly, but you will lose in generalization. Okay. So these are basically the two things that we might. There are many other things that we'd be interested in. These are two key ones. Okay, so what we would like to do, the type of results that we would like to have is something like if we have, let's say we have a learning algorithm, it uses a hypothesis class age, okay? What can we say about its generalization error, okay? So we'd like a result that tells us if we use n samples, what is the generalization error? Is that clear? Or elaborate? Because of the hat? Really? Okay. Okay, so we'd like a theorem saying something like if ERM uses n samples, then its let's call it ETH-ERM S would be less than, say, epsilon. Okay? That would be nice, right? If we could say, okay, I have some epsilon, let's say 0.01, okay? And let's say there is a theorem that tells me if you use more than 10,000 examples, your error will be less than 0.01. That'd be nice, right?
But it depends on the hypothesis class.
Obviously, but okay, I'm saying this would be a nice theorem to have, right? This is sort of what we want. Sorry?
No, I said Chebyshev.
What?
Chebyshev, like just
Chebyshev. Well, yes, it's going to go there eventually. Okay? So I'd like something like that. Do you think this is possible? Can I have? Okay, let me just constrain ourselves to the case, the ideal case where the rules that the hypothesis that we work with is actually contains the true rules. Okay? Right? So this setting, not this setting, this setting. Okay? So it's realistic to talk about zero error. Okay? Okay, so think about it for a second. Do you think we can come up with a theorem like that?
No.
Why not?
Because it always depends on the real rules that I don't know. We have to make assumptions before we can say.
Okay, so I said we will assume that okay, so let's assume okay, so you're right, generally impossible to have a theorem of that strength. Okay? one reason is that you say, okay, the true rule might be outside our context class, so there's no way we can achieve an error as low as we want. Okay? You're right. So let's assume that the true classifier, let's say, is in H. Okay? So the red rectangle case that we have. Okay? So this is called the realizable thing. Okay? So again, we're assuming that the rule that generates the labels, okay, is what? Is in English. Okay? Right? So this is a huge simplification for us, right? We assume that in a sense we know the true rule. On the other hand, it's not such a huge simplification.